use the PowerPoint notes, that's fine. There should be plenty of room there. Okay, so when we're talking about stoichiometry, again, we're going to be using the math that you've already used. But what we're going to be doing is we're going to be converting one thing to something else, which is different. So before, when you were learning about conversions, like you started with carbon, we went from like grams of carbon to moles of carbon to atoms of carbon, right? So like everything we did was just carbon or just carbon dioxide. But now what we're going to do is we're going to learn how we can convert moles or grams of carbon to moles of or grams of carbon dioxide. So we're going to be converting from something to something else. And the only way we can do that is through the balanced chemical equation. So we're going to kind of look at this through a fun way of cooking, right? So let's say you're going to make pancakes and this is what you needed. So what we can do is we're just going to change that recipe into cooking equation, I guess, a balanced cooking equation. So 1 cup of mix plus 3/4 cup of milk plus an egg makes 8 pancakes, right? And so same kind of thing, we're going to translate this into chemistry in just a second. So if we need 24 pancakes, then we have to increase the ingredients to do that, right? So it's kind of like you're making a double or a triple recipe, like we may have done this, but we can actually do this using chemistry. So let's use the same thing. So if we want 24 pancakes, and we need 1 egg for 8 pancakes, that means we need a total of 3 eggs. So if I said triple the recipe and the recipe had 1 egg, you would be like, oh, I need 3 eggs. But the actual brain math that you're doing is you're doing this, you're just doing it in your brain. So we're going to be doing that exact same thing with chemistry, but we need to actually use chemical equations. So it's not so easy to do in our brain necessarily. Okay. So the thing about stoichiometry is you have to figure out where you're starting and where you're going. So you're always starting with something and you're always converting it to something else. And the way we go from one thing to another is always going to be through a balanced chemical equation. So the way you need to know that you need to know if you need to do stoichiometry is if they give you something, but they ask you for something else. The only way you can do that is look at a balanced chemical equation. So for example, here's an equation that we've seen a bunch of times. So nitrogen plus hydrogen makes, oh, what's that thing called? Ammonia, right? That was one of them we just had to remember, ammonia. And so this equation shows that for every 1 nitrogen, we need 3 hydrogens and we'll make 2 ammonias. So if we look at this factor right here, so if we look at our hydrogen to our ammonia, for every 3 moles of hydrogen, we have 2 moles of NH3. So do you see how I just took these factors and I made them into a unit conversion? So just like before, we could also write it like this. 2 moles of NH3 over 3 moles of hydrogen. And so this is that new unit conversion that we're going to use. And again, it happens when we have something, but we need something else. And so we can use it as, like I wrote it as moles. You can write it as molecules. You can write it as dozen. No matter what, the ratio between hydrogen and nitrogen is always 3 to 2. And so we're going to practice on how we're going to use that in just a second. Okay, so here's an example using chemistry. How many moles of iodine are required to react with 0.492 moles of aluminum according to the equation? Okay, so the thing about balanced chemical equations is they are the roadmaps to everything we do in chemistry. So sometimes people look at them and they're like, oh yeah, look, balanced chemical equation. No. Balanced chemical equations are everything in chemistry. They are the roadmap. What do I mean by that? So you see how it says how many moles, oops, how many, it doesn't want me to write. How many moles, doesn't want me to write. Let me write, there we go. How many moles of iodine? It has a mind of its own. How many moles of iodine? So what we want are moles of iodine. Should it moles with a question mark of this. And then look at what are we given? 0.429 moles of aluminum. So we have 0.429 moles of aluminum. And so what I mean by this is our roadmap is we have aluminum, but we want iodine. So that means we need to convert from aluminum to iodine. This is what stoichiometry does. It converts from one thing to the other. So we need to know what is the relationship between aluminum and iodine. Well, how many moles of aluminum do I have in my equation? Two. So it's 2 moles of aluminum to how many moles of iodine do I have? 3 moles of iodine. Now, I might use the mole ratio written like this, or again, I could just flip it. 3 moles of iodine to 2 moles of aluminum. So because we're given aluminum and we want iodine, we need to convert from aluminum to iodine. That's called a mole ratio, or people call it a mole-mole ratio. And again, we have to look at the balanced chemical equation, and we might use this one, or we might use this one. All we know is somewhere we're using one of those, because that's the only way we can convert from something to something else. So if we start with 0.429 moles of aluminum, we're at moles of aluminum. Which one are we going to use? The one on the left or the one on the right? The one on the right, because the moles of aluminum are on the bottom. So there's 2 moles of aluminum to 3 moles of iodine. And then all we need to do is multiply, divide by 2, and we get, was that 0.644 moles of iodine. And this is that new factor. This right here, this is our mole ratio. That's the only new thing. That's the one of the new things that we're going to do. Yes.
So you just get like the number that's on the mole ratio.
To get the mole ratio, you look at the coefficients in the balanced chemical reaction. That's where the numbers are always going to come from. And so because when you have something and you want something else, you have to do a mole ratio. Whenever you have something and you want something else, that means you have to get to moles. So you're going to see some problems and you're going to be like, oh my gosh, I don't know what to do, but they gave me something and I want something else. Well, somewhere in that problem, somehow you're going to do a mole ratio. So the thing you need to do, get 2 moles. Okay, so you're going to see that a few times. Like here is another one. So yes. Hold on one second. The 2. So this is iodine is I2. So what we care about is that there's 3 and 2. We're only looking at these. So like if we wanted a aluminum iodide, we'd look at this 2. So we only care about the stoichiometry, the coefficients, the things in the front. So like if we wanted to convert this to this one, AlI3, then we would have a mole ratio of 3 to 2 with that one. So let's try this one, because this one will be a great example of that. How many carbon dioxide molecules are produced when 0.75 moles of propane, propane is C3H8, is combusted along this equation? Okay, so again, once you see a balanced chemical equation, means you're probably going to use the balanced chemical equation. So we're starting with 0.75 moles of this. Okay, what are they asking for? Carbon dioxide molecules. When we see the word molecules, what should go in our brain? Avogadro's number, right? So when you see the word molecules in our brain, should go Avogadro's number. If you're like, that didn't go in my brain, it's okay, it will. It will. Okay, so, and we're starting with C3H8 and we're going to CO2. So let's say you have absolutely no idea what to do here, which is okay. But if we're starting with C3H8, does everyone agree? We've got to convert it to CO2. And the only way we can do that is using a mole ratio. So somewhere in this problem, we're going to use the mole ratio. How many moles of C3H8 are there? Yeah, there's 1 mole of C3H8. How many moles of CO2 are there? 3 moles of CO2. Somewhere in this problem, we're using that. Like that's a 100%. That's gonna happen. Now it might look like that, or we might have to reverse it. We just have to figure out which one cancels out our units. Okay, so in this case, what are we gonna start with? What number did they give us? Yeah, they gave us 0.75 moles of C3H8. Oh, well, hey, look, we already have moles. We already have it. So we can just go straight to our mole ratio. So which one's going to go on the bottom? The 1 or the 3? The 1. Yeah, the 1 mole. Oh, yep, hold on. I figured out how to fix that last week. 1 mole of C3H8, and then the 3 moles of CO2 will go on the top. Okay, does everyone understand where that ratio came from and why?
I don't understand why. I get it, it's the same one, but if you did it the other way, you would still be.
It is, but the reason we put the 1 on the bottom is so this unit cancels off with this unit.
It has to be
Exactly the same. Yeah, so the whole thing, so some people call this like, this is like, remember when you crossed off like your milliliters with your liters and your units had to match? It's that exact same thing now. We just have a new unit, but we gotta match our units exactly to cross them off. Okay, now, did they ask for moles? They asked for molecules. And so so when you're doing these problems, the key is don't say, how do I do this? Nope, is how do I go from this unit to the next unit I want? So I have moles. So everyone sees I have moles of CO2 right now, but they're asking for molecules of CO2. So in our brain, we have to go, can we go from moles of CO2 to molecules of CO2? And if the answer is no, that means we've got another step to do. Can we though? Yeah, because right, 1 mole of anything equals, who remembers the number? 6 times something to the something. 23rd, 6.022 times 10 to the 23rd molecules of CO2. So whenever you see molecules or atoms, that's the number that needs to pop in your head. By the way, I'll always give you that number. You don't need to memorize that number, but you'll use it so much, you will. So again, one side is going to go on the top and the other side is going to go on the bottom. We just have to pick it. Again, we need to match that unit perfectly. So which one's going to go on the bottom, the moles of CO2 or the molecules of CO2? Moles, because moles has to match, this unit has to cross off with this unit. The units have to cross off. So on the top goes 6.022 times 10 to the 23rd. I'm going to try and write all this on here. Molecules, I tried, molecules. And that's what we end up with in the end. And so each time you're doing this, this is what stoichiometry is. It really is just dimensional analysis, or like crossing off of your units. You're just following one after another after another. And again, in Chem 219, this is like 80% of the math, 80% of the stuff you're going to do is literally just variations on this. And so that's where we're going to practice it now. Oh, that's not what I wanted to do. Go back. Go back. Nope. Okay. And so here's it, not much prettier and nicer than my handwriting can do. It's the exact same thing, and with here is our answer. So in your calculator, you would put 0.75 times 3 times 6.022 E 23. All right, again, and this one is whichever way we've talked about this, whichever way your calculator makes you do this, right? And that should give you 1.4 times 10 to the 24th. Now, how many sig figs do I have in my answer? 2, because when I started with 2 sig figs, right? 0.75 is 2 sig figs, so when I finish, I need to have 2 sig figs. 1.4 is 2 sig figs. So sig figs are going to be a big deal, but don't even worry about them to get to your answer. Like just carry it, just pretend they don't exist. And then when you get to your answer, when you're about to like put like, this is my answer, you should go, oh shoot, sig figs. And then you go back and figure out your sig figs. You just ignore them till you get to your answer. Okay. You ready to try one? Okay, so you can try this one. So set this one up, go all the way to your sig figs, and then we'll go through this one together in just a minute. Okay, so we look at this. What are we starting with? What are they giving us? 4 moles. And again, this is our roadmap. They're giving us 4 moles of that. But they're asking for what? Molecules. Oh, so harder than moles. I can spell molecules. Maybe. So they're asking for molecules of NH3. So they're giving us this, but asking for this. So whenever they do that, that's the signal that we have to do a mole ratio. And they give you one thing, but they ask for something else. We've got to do a mole ratio. So somewhere in this problem, who knows where, we're going to have to use this. 1 mole CaOH 2 moles of NH3, right? Somewhere we're gonna have to use that. So we're gonna start with this, do our mole ratio, and let's see what we, oh, I didn't have this one down. So we have 4 moles of CaOH2. Okay, what unit has to go on the bottom? Yeah, 1 mole of CaOH2, which means that 2 moles of NH3 go on the top. Everyone agree with this step? Yes. We got this? Okay, so now if the question had asked us for moles, we'd be done. But it didn't. It asked for molecules. Why? Why? So in 1 mole of anything, there are 6.022 times 10 to the 23rd molecules of it. Okay, so when we do this, by the way, how many sig figs will we have in our answer?
2.
2. Okay, so what did we get? 4.8 times 10 to the 24 molecules. Let me just spell this so you can read it. Of NH3. How are we feeling this? Good? And if you got that, that means you and your calculator are friends. So this is a good thing. Again, make sure when you're doing your homework and you're doing your quizzes, when you're doing an exam, always use the same calculator. I literally just graded an exam this last week where every single question was so wrong, but every process was so right. It was just your calculator. It's very frustrating to grade, right? It's not what you want. It wasn't in this class. And it's because the person had to get a new calculator for the day of the test. Yeah, had to borrow one that she didn't know how to use. So always have the same calculator the entire time. Okay, this is a fun one because does anybody ever get to watch the rockets launching from Vandenberg? And we see like no, they come right over us at night and during the day. So
Is that all the streams
some of them when they're launching the SpaceX rockets. So when they do that, they're using hydrogen. So if 1.8 times 10 to the 8th grams of hydrogen is used during liftoff, then what is the mass of oxygen consumed? Okay, so when we're looking at this, we're starting with what? Grams of hydrogen. So we're starting with grams of this. And what are we going to? Grams of oxygen. Okay, so we're going to have to convert. So we know we're starting with hydrogen and ending with oxygen. So that means that we're going to have to use the mole ratio between them. So how many moles of H2 will we have? 2 moles of H2 to how many moles of oxygen? 1 mole of oxygen. So how we do this problem, I don't know, but I do know that we have to do a mole ratio somewhere in here. And so since we have to do a mole ratio, that means we have to get to moles. So if we're starting with grams of hydrogen, well, can we get from grams of hydrogen to moles of hydrogen? How do we go from grams to moles? The mass, the periodic table, we look at the molar mass, right? And so this part right here, we're gonna start at grams of hydrogen and go to moles of hydrogen. That's using our molar mass, right? So our molar mass. Now, after we do that, then we can use our mole ratio, which we have here, and we're gonna be at moles of oxygen. But did they ask for moles of oxygen? What they asked for? Mass of oxygen, grams. Can we go from moles of oxygen to grams of oxygen? Yeah, moles to grams, again, molar mass periodic table. Okay, so let's go through these units. How many grams of hydrogen are in 1 mole of hydrogen? But there's 2 hydrogens. So that means there's 2.016 grams of H2 in 1 mole of H2. Everyone see why we had to multiply that by 2? Same thing. Let's look at oxygen. How many grams of oxygen are in 1 mole of oxygen? 16, but there's 2. So it's going to be 32 grams of oxygen in 1 mole of oxygen. Careful of those, right? Careful of those. It happens all the time.
That's where we do have to pay attention.
Yes. Yeah. Okay. So if we start this, if we start with bottom. So it depends on if we're doing a mole ratio. So if you've got, and what do I mean by that? Like, it's going to help you. Let me try this with another green. So whenever you have moles over moles, you only look at the coefficients in front of the reaction. If you have moles over moles, you only care about the coefficients. That's all you're looking for. You're only looking at a balanced chemical reaction. But if you're going from grams to moles, that's just like we did before. So when you go from grams to moles, we always look at the periodic table. And then remember the definition of the periodic table, that's the number of grams in 1 mole. So like if I said, go get me a mole of hydrogen, you would bring me 2 grams of hydrogen. If I said, go give me a mole of oxygen, you would get me 32 grams. So you have to pay attention to all of the little numbers when you're using moles to grams. Does that make sense? So it's kind of like, that's why the units are so important. So when you're looking at your periodic table, you just add it all up. But when you're looking at just these coefficients that are in the balanced chemical equation, a mole over mole, that's all you're looking at. Okay, let's see if I can change my color back. Oh, look at who's getting kind of good at this. All right, so let's try this. So if we have 1.8 times 10 to the 8th grams of hydrogen. So again, even if you're like, I'm not sure where to go from here, we just know we have to get rid of hydrogen, right? Everyone agree?
Yes.
We have to get to moles. How do we go from grams to moles? Periodic table, right? So there's 2.016 grams of hydrogen in 1 mole of hydrogen. So this again, this is the periodic table. This is the stuff that we've done before when we were going from grams to moles, moles to grams, moles to molecules. Now we can do the new piece. So our new piece right here, there is what unit has to go on the bottom here? H2. There is how many moles of H2? 2 moles of H2 to 1 mole of oxygen. Again, we're only looking up here at the coefficients. So when you have mole over mole, we only look at the coefficients. Okay, but now we're done with the coefficients. We've got oxygen, which is what we wanted. But we have moles of oxygen. We want grams. How do we go from moles to grams? Periodic table. Yeah, in 1 mole of oxygen, there are 32 grams of oxygen. Okay. How are we feeling on this? Seeing how important these units are? Really, the numbers are just there. The numbers are there to help us with our units, right? Okay, so when we do this, oh, well, I almost made it. You end up with 1.4 times 10 to the 9th grams of oxygen. Tried to make it so I had room, almost had room. Here it is, I'll just leave it prettier. So you can see each time, oh, go back. Our units, grams cross off grams, moles with moles, moles with moles, and we're left with grams. So the units are essential when we're doing stoichiometry. So again, there's only one new piece here. It's just this. Everything else we've done before, we're just putting a new conversion in it. Does that make sense? How this is this mole-mole ratio, it's just our new piece. Okay, you ready to try one? Maybe. How's your by the way, if you get this in your calculator, you guys are BFFs. You got this. You can do this, you can do anything in your calculator. So make sure you put this in your calculator because you're using your exponent buttons and you're dividing by more than one number. It's a lot all in one calculation. So this really tests your abilities. This one, if you're able, you have your calculator. Just see if you get, by the way, this won't work on a phone. You will not get the correct answer. How are we doing on that? Okay, all right. Give you another second to practice this one on your calculator, making sure you're getting this specific number. If you're getting the number, if you're getting this number, but you're getting 10 to the 8 or 10 to the 10, let me know because it means you're doing your exponents incorrectly from your calculator, which happens kind of often. Okay, ready for trying one all on your own? Okay, same thing. But this time, I want to know how much water vapor is produced. So last time we talked about, well, how much oxygen do we need? But this time we were going to go to water. So same type of problem, but I want you to try this and set it all up with those units and put it in your calculator and see what we get. And then we'll go over it in just a minute. Okay, so let's look at this. How did we do? 1.6 times 10 to the 9. Yes. Got this in your calculator? Yes. So again, in your calculator, what you're going to put, depending on how your calculator works again, right? It's going to be 1.8 times 10 to the 8th times 2 times 18.02 over 2.016 times 2. And again, some of your calculators are going to want parentheses, some don't. It's just whichever way you and your calculator work.
So I have a question on the mole ratio.
Mhm.
Since those cancel each other out, could you simplify it to 1 to 1?
No, it's important. Don't simplify the mole
Don't.
ratios.
Okay.
Yeah, such a great question. So this mole ratio here was 2 over 2. Don't simplify the mole ratios because when you start simplifying them, it just introduces like errors later in time. Because then you're like, well, can I simplify this? Nope, don't do that one. So just leave them as is. Okay, so this again, what we just did here is stoichiometry. This again, periodic table. Periodic table. This is our new unit that we're introducing. So it's just one new thing using a balanced chemical equation to do it because we went from hydrogen to water. And again, this is what we're going to spend a lot of time on. God, for the rest of the semester, we're going to be doing this kind of stuff. And it's new now, but you're going to have so much practice. So much practice. Okay. So this is again stoichiometry. So what we're going to do now is we're going to look at reaction yield, but we're not going to do anything new. We're not going to do anything new at all here. So when we do this, we're going to look at, so let me just go to this problem right here. So in the problem we just did, we started with hydrogen and we converted to water, right? So we're saying, hey, given this much hydrogen, here's how much water we're gonna make. But what we're gonna look at next is, what if they gave us hydrogen and they gave us oxygen? Well, how much water do we make then? So that's what we're gonna look at now with these yields. And so what we're gonna do is we're gonna look at reactants to figure out how many products we're gonna make when we mix them. Okay, so we're gonna do it with something that's fun. Cheese sandwiches. Okay, so we're just gonna make normal basic cheese sandwiches. You get 1 slice of cheese to 2 slices of bread, right? Just very conservative cheese sandwiches. Okay, so if you have 28 slices of bread and 11 slices of cheese, how many sandwiches can we make? 28 slices of bread, 11 slices of cheese. How many sandwiches can we make? 11, right? Does everyone agree?
Wait,
28 slices of bread and 11 slices of cheese. How many sandwiches can we make? 11, right? Because after we use the 11 slices of cheese to make our cheese sandwiches, we don't have any cheese left. Everyone agree? Do we still have bread left? We do, but can we make any more cheese sandwiches? No, that's what we mean about using the reactant. And so in this case, if we change this again into like a chemical-ish equation, for every 2 bread slices, there's 1 cheese slice. So if we have 11 cheese slices, that's the one we run out of first. We're going to call this our limiting reactant. We can only make 11 sandwiches. So that's what you just did in your head. You looked at, you're like, oh, I have 28 slices of bread and 11 slices of cheese. I can only make 11 sandwiches. I have extra bread. Cheese is what's limiting the number of sandwiches I can make. Cheese is my limiting reactant. So every time you cook, it's kind of the same thing that you do. We're just going to do it with chemistry. And so if we're given more than 1 reactant, we have to figure out which one gets used up first. Now, if we used all of our bread, how many sandwiches could we have made? 14. But is there any way, given what we have for this problem, we could have made 14 sandwiches? No, that would have never happened, because after we made 11 sandwiches, we had no more cheese. And so the limiting reactant always determines how much product you can make. Cheese determined how many sandwiches we could make. We only got to 11 sandwiches. We could not make 14 because we had no more cheese left. So in these limiting reactant problems, you're going to be given 2 reactants. One of them is going to get all used up. The other one's going to be excess or extra. In this case, bread was extra. We don't care about the bread. It's not the one that's going to determine how many sandwiches we can make. So again, cheese is our limiting reactant. Bread is the excess reactant. So whenever we're given 2 reactants, we need to find out which one is our limiting reactant. So the limiting reactant will always be entirely consumed. So it limits the amount of product we can make. We could only make 11 sandwiches because we only had 11 slices of cheese. So we're going to do the exact same thing. We're just going to do it with chemistry. First, we're going to look at a picture. So here's the picture, just for those visual people. We had 28 slices of bread and 11 slices of cheese. So when we do this, we can make 11 sandwiches. And then we just have a bunch of extra bread. We could have never made any more, right? So this is what you did. You just did this in your head. But with chemistry, you can't really do it in your head. Too many numbers. We're going to have to actually write it out. Okay. So let's look at an actual chemical equation. So hydrogen plus chlorine makes HCl. If we have 3 moles of hydrogen and 2 moles of chlorine, how much HCl can we produce? So again, they gave us a chemical reaction, which means we need to use the chemical reaction. So in this case, we have 3 moles of hydrogen and 2 moles of chlorine. Okay, so what are they asking us to find? HCl. Okay, so when you have a limiting reactant problem, the first thing to realize is that it is a limiting reactant problem. How you can tell it's a limiting reactant problem is when you're given two reactants. If you're given two reactants, one of them is going to get used up first. So that's how you know it's a limiting reactant problem, is you're given two reactants. If you're only given one reactant, you just do exactly like we just did. But if there's two reactants, you do exactly what we just did twice. So there's really no difference. You just have to do it twice now. Okay, so here it is. Here's with hydrogen. I just converted moles of hydrogen to moles of HCl. Everyone good with this conversion now? Now I'm going to do the same thing with chlorine. I took chlorine and I converted to HCl. So on the problems we did before, we only did this one time. When there's a limiting reactant, you have to do it 2 times. Same exact thing, you just have to do it twice. Now, one of these is real, and one of these never happened. It's imaginary. Okay, how can we tell? Well, when we used all of our hydrogen, we could make 6 moles of HCl. When we used all of our chlorine, we could only make 4 moles of HCl. Which one are we going to run out of first? Chlorine. So do you see how chlorine could only make 4 moles of HCl? So that means after we made 4 moles of HCl, we had no chlorine left. So that means we could have never made 6 moles of HCl because we had no chlorine left, right? So if we look up here, this reaction, after we made 4 moles of this, we had no chlorine. If we have no chlorine, can we make any more product? No. So that means that this one on the top never happened. It's imaginary. So yes, you're going to do 2 problems, but you're only going to use 1. Now, when you're doing these, you don't need to like cross it out, be like, oh my gosh, no, you don't need to do that. You just need to be like, yep, not using that one. So this is our answer. What is the limiting reactant is our chlorine. So when we look at this, the limiting reactant always makes the lesser amount of product. So do you see how 1 made 6 and 1 made 4? 4 is less, that's our answer. Now, the question I get a lot of times is, which one's my limiting reactant? And people will be like, oh, HCl. So we abbreviated LR. HCl is my limiting reactant. Quick question, is HCl a reactant? It's a product. So our limiting reactant, we only have 2 options. It's either hydrogen or it's chlorine. The limiting reactant is the one that we started with. So chlorine is our limiting reactant, right? And so the one we start with, that's our limiting reactant because it has to be a reactant. And the amount we can make is the rest of that stoichiometry problem. So again, we're not doing anything different than you did before. We're just going to do it twice. You just do it 2 times and you have to pick an answer. A lot of times people are like, I get this. And I'm like, awesome, but you have to pick one. You got to be like, nope, yeah, that one's my answer. You got to pick one. So you're going to do the same thing you did. You just got to pick your answer now. Okay. Nope, that's not what I wanted to do. Okay. Here we go. Oof. This one's for you to practice. 2.3 times 10 to the 8th grams of hydrogen and 1.5 times 10 to the 8th grams of oxygen is used in the liftoff during a shuttle launch. What is the mass of water produced? So we've already seen these problems, but this time we have grams of hydrogen, right? We have grams of this. I'll actually write the number. 2.3 times 10 to the 8th grams of this. And we have 1.5 times 10 to the 8th grams of this. And we want grams of water. So we're given two reactants. What do we have to do? One of them is going to get used up before the other one. So this is a limiting reactant problem. So whenever you're given two reactants, you got to do two problems. So that means we're going to convert hydrogen to water, and then we're going to convert oxygen to water. And then we have to pick our answer from there. So it's the same thing. You just have to do it twice now. So try this and we'll go over this in just a couple minutes. Okay, let's see what we got. Okay, did you get 2.1 times 10 to the 9th grams of hydrogen? And our next one is 1.7 times 10 to the 8th grams of, or sorry, grams of water. Grams of water I meant for both of those. So if your conversions do not look like this, where did you make a mistake and how can we fix that? So the most common mistakes would people be using just one hydrogen and one water. So using 16 and 1, that would be the most mistakes. And the other mistakes are in the unit conversions. So again, when we're doing these unit conversions, we have to make sure that this unit is the exact same as this unit. Whenever you have grams, the only way to get rid of it is the periodic table. So these are both using the periodic table. This is our new unit that we use today. This is our mole-mole ratio. This is again is what we did before. These two are our periodic table. So whenever you have grams to grams, you're always going to do that same three. Periodic table, mole ratio, periodic table. Every single time it's grams to grams. Yes. Sometimes luck's amazing. Sometimes as long as, so if you got this same answer, that means you had these units, you just didn't have them quite in the right order. But that's okay. As long as your units are crossing off, they don't have to be in the right order. Okay, so we got both of these answers, but only one of these answers we're going to use. The other one's just extra work. Which one is the one we're actually going to use? The bottom one, the 1.7, right? Because we made 1.7 grams of water and then we ran out of what reactant? Oxygen. So that means oxygen is our limiting reactant. So again, this one never happened. It's imaginary. So we have to pick an answer. And again, you don't need to black that out, just a little mark. And by the way, so if you look at our video limiting reactant videos like online, there's like at least 3 or 4 different methods that people have used for using limiting reactants. This one I've just found as the simplest. It's a little bit more writing than the others, but it's the most direct method. So, but if you have a different method you want to use, you can absolutely do that. But when you watch videos, just know that there are other methods out there. Okay, so this is limiting reactants. Same thing we did, just do it twice. Okay, any other questions on this? Or feeling more comfortable? Yeah, yes. So if we look at this one up here on the top, so I'll look at this one. So in your calculator, again, depending on which calculator you have, so yours likes entire top divided by entire bottom. So on your calculator, parentheses 2.3 times 10 to the 8th times 2 times 18.02 parentheses divided by 32. If you don't use the parentheses on the calculator, what happens is it takes this 18.02 and it only divides it by 32. It doesn't take the entire top. So that's why you might need the parentheses. If you have the calculator that does the fractions, then you don't worry about it because you just put the fraction in. But if you don't have the calculator with the fractions, you probably need to use these parentheses. Otherwise, it's not multiplying the whole thing. Or you can just do what I do. I take the entire top and then I just hit enter. And then I divide it by the bottom because I don't like parentheses. Yeah. Okay. Feeling better about these a little bit? This is what our homework is this whole week, is doing this again and again and again and again and again. Yes.
So what we're talking about, oxygen is like, we're looking at the number on the right.
Yes. Oh, so the one on the top, so we started with hydrogen and then we converted it to water. That's this one right here. We started with hydrogen and we converted it to water. And then the one on the bottom is we started with oxygen and converted it to water. So we start with oxygen and then convert it to water. So it's two separate problems that we have to do. Does that make sense? And then how we tell which one is our answer is we look at which one is smaller. So this is smaller, so that's our answer. This one's imaginary, never happened. Is that more clear? Okay, so this is stoichiometry. All stoichiometry is pretty much the exact same thing. It's just introducing that new unit of mole ratios. So the next thing that we're going to do is theoretical and actual yields. Every single thing that you've calculated and looked at your periodic table, those are called theoretical yields. We just didn't call them that. But by the way, you just done like 10 theoretical yields. So theoretical yield is when you have to look at the periodic table. If you ever have to grab a molar mass, you're doing a theoretical yield. Okay. Now in lab, which we're going to do, we're going to get the actual yields. So the actual yield is the one you get when you actually do the equation in real life. So when you actually mix the chemicals and weigh them and react them, that's the actual yield. The theoretical yield, that's how much, if you did a perfect job and it was a perfect reaction, they should be the same. They are never the same. They're never, ever, ever going to be the same. Okay, so how we figure out the percent or the actual yield and the percent yield with the theoretical yield is we use this. Percent yield is the actual over theoretical. The percent yield is how close did you get to the theoretical yield, right? That's what the percent yield is telling us. How close did we get to what we should have gotten? And I always remember because it spells at, actual over theoretical times 100. This is the one in lab that we get. This is the one that we get by calculating. I always think if I look at my periodic table, that's a theoretical yield. So what you just did in that last problem is you did two theoretical yields and you only used one of them. So an important thing to remember is yield means product. Yield means product. So when we're doing percent yield, it's always the actual yield. Yield means the actual product, the theoretical product. So if you're given a reactant, you can't use that. Have to convert the reactant to product. Let's look at an example of this, which you get an answer on there. Okay, upon reaction, 1.24 grams of copper sulfate with excess zinc metal, 0.392 grams of copper metal was obtained according to this equation. Okay, so let's look at what they give us here. 1.274 grams of copper sulfate. 1.274 grams of this. Okay, it says excess zinc metal. What does that mean, excess zinc metal? Extra. You know what excess means? Ignore it. That's what, ignore. That's all excess means, ignore. And then it says that 0.392 grams of copper was obtained. What is the percent yield? Okay, so remember, percent yield is always going to be actual over theoretical. Okay, but they're both products. Are we given two products? No, we're only given one product. So what people will do is they'll try to divide these two numbers, but we can't because this one is a reactant. Can we convert this one to product? Can we convert copper sulfate to copper? Yep, we can do that doing our stoichiometry. So when this one says that the 0.392 was obtained, that means they got that from lab. So they actually mixed these two things together and they got 0.392. So if they got this from lab, is this 0.392 the actual yield or is it the theoretical yield? This is the actual yield, right? So this is our actual yield. So which one do we have to find? We have to find the theoretical yield. And to find the theoretical yield, we need to convert these two. Okay? All right. So to convert these two, we're going to need some molar masses. Okay, so when we do this, we have to start with 1.274 grams. Now, we're going to convert from grams of copper sulfate to grams of copper. What's the mole ratio between the two of those? There's 1 mole of CuSO4 to 1 mole of copper. Right? So somewhere we're using this. Is that going to be our first conversion? What do we have to do before we do that? We have to go to grams. So if we have 1.274 grams of copper sulfate, we need to get rid of the grams of copper sulfate. You get 159.62 grams of copper sulfate in 1 mole of copper sulfate. How did I get this number? I looked at the periodic table. Right, so that's the periodic table. Now, what can we do? Now we can use the mole ratio. So do you see how we're going from grams, and then we're going to go to grams? How many train tracks will we need if we go from grams to grams? 3. Always 3. If we're going from grams to grams, we need 3. So we did 1. So the next one's our mole ratio. 1 mole, I forgot the copper. To 1 mole of copper. What's our third train track going to be? Molar mass. In 1 mole of copper, there's 63.55 grams of copper. Again, periodic table. Mole ratio, periodic table. So once you start feeling comfortable with these, you kind of fly through these. But I want to warn you, when you get comfortable with these, that's when you start making mistakes. So it's okay to fly through them, but fly through them slowly. Okay, so you don't make the mistakes. Okay, so we get 0.5072 grams of copper. Okay, so when we do this, again, our percent yield is going to be actual over theoretical. What is this one? Is this one 0.5072? Is this our actual yield or our theoretical yield? It's the theoretical yield. Our actual yield was given. So actual over theoretical times 100. So that means that our 0.392 goes on the top and our 0.5072 goes on the bottom, and our percent yield is 77.3%. So if everything went perfect, this would be 100, but it never goes perfect. And so we got close though. 77 is pretty good percent yield. That means we did our lab pretty well. Unless you're in lab, the actual has to be given to you because there's no way for you to get it. Yeah, so in these problems, the actual yield always will be given because, well, we're not in the lab. So in the lab that we're going to do, we're going to actually do, and by the way, in 219, you actually do this. You actually do this lab and you figure out your percent yield. And we're going to be doing that again. We do with the percent hydrates. We do the same kind of thing. Okay. So we're gonna, let's take a break. So we're not gonna talk about titrations yet. We're gonna do it at the end. At the last couple weeks of class, we'll talk about titration. So we're gonna skip that. So when we look at chemical, when we look at this, hold on, why is this not working? Doesn't want to. Oh, let me just work. There we go. Okay, so when we're looking at these reactions, there's acid-base neutralization reactions we've talked about. It really is just incorporating solution stoichiometry, and then precipitation reactions. That is just exactly what we just did. So what we're doing is we're just gonna incorporate molarity into these things. So just as a reminder, molarity is moles of solute over liters of solution. So what we're gonna do now is we're gonna incorporate that into our unit conversions, into our stoichiometry. Okay, so when we look at solution stoichiometry, we're gonna do mole ratios and we're gonna do molarities all in kind of one piece now. So let's look at this. Here's an example of solution stoichiometry. How much 0.125 molar sodium hydroxide solution do we need to completely neutralize 0.025 liters of 0.175 molar sulfuric acid solution? Whew, right? It's like a lot. But again, the key is that balanced chemical equation. That's the roadmap for our problem. There's so many numbers. It's just like, I can't. My brain's like, no. Put the numbers on the balanced chemical equation to figure out what you have and what you want. So we have 0.125 more of this. 125 molar. And then we've got liters and molarity of this. So we have 0.025 liters of this and 0.175 molar of this. Okay, and how much do we want? Oh, we want the volume of this. So liters, right? It says how much? Liters, maybe? Do you see how I just took all of those words and I put them on the balanced chemical equation? So now if I took all of these words out, I'll put this back. I'll make it so you can see it in a second. But really, all we need is that chemical equation now. A lot of times when you see these problems and people just read the problem again and again and again, they're like, if I just keep reading it, the answer will pop out. No, that's never happening. It's never happening. You got to take the numbers out and you got to put the numbers on the roadmap and then you can figure it out. Okay, so let's say we did that and we're like, I don't have any idea what to do. Remember, when we look at molarity, molarity is 2 units. It's moles over liters, right? So when we look at this molarity, molarity has 2 units. If we have the choice to start with 1 unit or 2 units, what should we start with? 1 unit. Always start with 1 unit. Can you start with 2 units? Yeah, but it makes it so much harder. Okay, so of the numbers we're given, so we're given liters and 2 different molarities. Which one only has 1 unit? Liters. Start with that number, right? And so a lot of you, when you text me and I send something back and I'm like, this has 2 units, this has 1 unit, start with 1 unit. So if we start with just liters, 0.025 liters H2SO4. Okay. Well, we know we want to get rid of liters, right? I don't know what we're going to do, but I don't need it. So now if we look at this number right here, just as a reminder, I'm going to put this all the way down here. 0.175 molar H2SO4. This means 0.175 moles of H2SO4 in 1 liter. Everybody remember that when we did molarity? That's what 0.175 moles means. It means this many moles in 1 liter. So can I rearrange that unit? Can I rearrange this to fit into this next thing? I can, right? I can just take this and put it right here. In 1 liter, I have 0.175 moles of H2SO4. So this part we've done before, right? So we've gone from liters into moles using molarity, right? That was our last homework, I think, or last 2 homeworks we did. Okay. So now we have H2SO4, but what are they asking us for? NaOH. We have something, but we want something else. What are we going to have to do? A mole ratio. Like every time we have something and we want something else, we've got to do a mole ratio. So we're going to be doing a mole ratio in between our H2SO4, there's one of those, to 2 NaOHs. Which one has to go on the bottom? H2SO4 has to go on the bottom, 1 mole of H2SO4, because these units have to cross off. So if our 1 mole of H2SO4 goes on the bottom, what's going to go on the top? 2 moles of NaOH. And again, that's coming from our balanced chemical equation. And the reason we had to do this is because they gave us H2SO4, but asked for NaOH. So in the middle, we have to do a mole ratio. Okay. So now we want to get to volume of NaOH. And we have 1 unit left, 0.125 molar. Yes. Now, when we look at our next one, 0.125, again, that 0.125 means 0.125 moles of NaOH over 1 liter. Do you see a way that we could use that in here? Yeah, if we put the moles of NaOH on the bottom, 0.125 moles of NaOH over 1 liter. And our units cross off. What were we looking for in the end? Liters. What do we have? Liters. So all we did was follow our units through, use all of the units they gave us, and we end up with the unit we wanted. Yes.
Because it doesn't tell us how many liters.
Yeah, so that's a definition of molarity. So 0.125 molar means that many moles in 1 liter. Yeah, so it's like the definition of it. It's always over 1 liter. Yeah. Yeah, whenever you see big M, it's moles over 1 liter. Every time. Yeah. Always 1. Okay, and so when you look at this, let's look at it neater. I think I have it neater. I do. So here's the whole thing, neater. After I erase for a minute or 2 here. So we use this again. Now this right here is 0.175 molar. That's what that conversion is. This is our mole ratio. And then again, we used our molarity. This again is 0.125 molar. So what we did right now is we incorporated molarity into our stoichiometry. So whenever you see stoichiometry, that means you're using the mole-mole ratio. We just put molarity in with it now too. So we've already done molarity. Now we've already done mole ratios. We're just putting them together, right? And we're putting them together in one equation. And when we put that equation together, our units cross off and we end up with volume of our solution. Okay, more so. You see how important the units are here? They're like impossible to get these right without the units. You have to be very careful with the units. Now, when you're using these units, H2SO4, that's going to be important. It's not just moles, it's moles of H2SO4. It's not just NaOH, moles of NaOH. You need the moles and you need the label. They both need to be there with stoichiometry. And I know some people are like, oh, I don't want to write all that. Trust me, I'm saving you hours of pain and agony to write it now, because no matter what, you're going to have to do it later. So we might as well just get used to doing it now. Okay, so let's try another one of these. Okay. So what I want you to do is I want you to take those numbers and put them on the right, in the right place on the balanced chemical equation. So take the numbers out of the problem and just write them like wherever they go. Do they go here? Do they go here? Do they go here? Like, where do they go? Just identify where the numbers go. And let's see if we can, let's try that's the first step. See if you can put them in the right place on the balanced chemical equation. So put them on the roadmap. Is this one not on there? Oh, well, then you get your whole thing down. This is a new one. Sorry. All right, so the 50 milliliters is going to go with who? HCl. Worry about my sig figs in the end. 35.23 is going to go with what? NaOH. And then 0.250 M goes with NaOH. Okay, now what do we want in the end? Molarity of HCl. Remember, molarity is big M. We want the molarity of this. So in the end, we want molarity of HCl. So remember, molarity of HCl means moles of HCl per liter. So it goes to NaOH. So see how this says 35.23 milliliters of this? So that means that they're going together. So that's how we know that 35.23 goes with the NaOH. Okay, any other questions about where everything went? Okay, so now we got three numbers again. We got 2 milliliters and a molarity. So the milliliters only have one unit and the molarity has two. So we have two choices. We could either start with the 50 or we can start with the 35.23. So everyone see that those are kind of our two choices here to start with. Okay, so if we start with the 50 milliliters of HCl, not sure what to do. Okay.
I thought we didn't start with one if there were two.
Yes, so we have to decide which one to start with. So we're given, what are we trying to convert to? Molarity of HCl. So we have all this information about NaOH and we want to convert it to HCl. So should we start with the volume of the NaOH, the 35, or should we start with the volume of the HCl? Okay, well, let's try. If we start with 50 milliliters of HCl, where can we go? We could go to grams. We could go, but to get to grams, we would have to have a moles, right? Do we have a moles? We want a molarity. We don't have a molarity. So there's, can't really go anywhere, right? Let's try it with the NaOH. 35.23 milliliters of NaOH. Where can we go here? Let me just do let's do this one. Yeah, let's go to liters. Right? That's something we can do. I'm just going to put this here for clarity. Okay. Liters HCl, liters NaOH. Okay. Can we do anything with the top one? Look at the bottom one. Can we do anything with the bottom one?
Bottom one, we have the molarity, so we can do the moles over liters.
Yeah, so do you see this bottom one? We have enough information to do something with the bottom one. Do we have any information with the top yet? No. So we're not gonna be able to start with this one. We're gonna have to start with this one down here. With our molarity in 1 liter of NaOH, there's 0.25 moles of NaOH. So in the future, if you're looking at a problem that has molarity and you're given both the moles and the milliliters, that's the one you want to start with. Don't start with the other one because there's just not enough information, right? We couldn't start with this one because we didn't have enough information. So we're not going to start with the 50 milliliters of HCl because there's not information to do. We don't have enough. We're going to start with this one right here, the NaOH, because we have enough information. So if you have a molarity and a volume, start there. So that's how we know to start with the 35.23, because that's the only one we have enough information with. Okay. We're trying to get to molarity of HCl, right? Well, right now we have moles of NaOH. Let's say we don't know what to do, but I want to put moles of NaOH here. Where's a way I can get rid of these moles of NaOH? Could do the little mole ratio-y thing, right? We could go from NaOH to HCl. How many moles of NaOH do we have? 1. How many moles of HCl do we have? 1. Oh, well, hey, at least now we're at HCl. We're making progress. Because remember, we want moles of HCl over liters in the end. Well, what unit are we at now? Oh, we're at moles. Check, we're at the top. How do we get the bottom number? Yeah, we're given 50 milliliters, right? They give us 50 milliliters. Can't we just convert that to liters? We can just convert our 50 milliliters to liters, and then we've got moles on the top and liters on the bottom. So you can do this all in one conversion, although some people don't like it. I'm going to show it to you in one conversion, then we'll do it in 2. If you do it in one conversion, then you just have 0.050 liters. And people are like, but there's nothing here. You just put a happy face. So you can do this, but some people are like, I don't like that. No, I don't want to do that. You don't have to do that. You can do the calculation, get the moles, and then divide it by the volume. So you could get the moles and then just divide it by the liters. I can't remember what you get for the moles, but you would divide it by 0.05 liters. So you can do it in 2, you can do 2 different ways in the end. This 0.0, this was 50 milliliters. And there's 1,000 milliliters in 1 liter. I just did it really fast. I just did that. Yeah. Right? 1, 2, 3. Yeah. So this solution stoichiometry, I think is harder than regular stoichiometry because molarity has 2 units in it and it's confusing.
So it wouldn't work if you just wrote 1,000 milliliter on top. You have to do the math before writing it.
Yeah, you kind of do. And that's why people are like, I don't like this way. No, thank you. And so when they'll do is they'll just do this and they'll get moles of HCl. And then you just plug that in down here in 2 separate steps. This is total preference. Okay, so let's look at this neater. So what did we do on this problem? So we started with the volume of NaOH, and then we used the molarity of NaOH. We started with 35.23 milliliters, and then we used the molarity, which was 0.25 moles over liters. Then we used our mole ratio, which was 1 mole of NaOH to 1 mole of HCl. And then again, we used our volume to get to our concentration. Doesn't want to work now. So here it is, because I can't do these both at the same time. Here it is when I just get the moles and do it separate. So here's the exact same thing. I'm just stopping at the moles. And we get 8.81 times 10 to the negative 3 moles. Okay, so then to do our molarity, we need moles over liters. So that's going to be 8.81 times 10 to the negative 3 moles over 0.050 liters. Well, with sig figs, we need to fix it still. I'm going to write again how I got those liters. So if you have 50 milliliters, there's 1,000 milliliters in 1 liter. That gives us 0.05 liters. Everyone see that? So we just put 0.05 liters on the bottom. Yes. You can do 2 separate. Yeah. So you can do it just like this where you get your moles and then divide by your liters. Yeah. And then when we do this, technology. There, no, it works and then it doesn't work. So when we do this, we end up with 0.176 molar. And again, that molar is 2 units. I just did this in whole, I just put the conversion over here, which I know is kind of confusing for this one. So just ignore this. Ignore this one.
In my head, but you got the 3 based off of. I see 4.
Yeah, so great question. Why is this 3 sig figs? So how many sig figs is the 50.00? 4. How many sig figs is 35.23? 4. How many sig figs is 0.250? 3. So that's why we have 3 sig figs in our answer. So 0.1763 significant figures. Yes. So from the periodic table, the only time you can use the periodic table is if you have grams with it too. Because the definition of the periodic table, that's the number of grams in 1 mole. So we couldn't use the periodic table in this case because there are no grams in the problem. So the only time we can use periodic table is if there are grams as one of our units. And this time our units were only liters and milliliters and moles. Sometimes we'll use both, which you'll see in a minute, but sometimes we'll use both. But yeah, so the grams and the moles have to stay together. That's always 1 unit together, grams and moles. Okay. So I want you to try this one. So super similar to what we just did, just a different, is this one on there?
Yeah.
Okay, this one's on there. So try this one and we'll go over it in just a couple minutes. Let's look. All right. One mole ratio. And then I did it all in one, but you don't have to, but did you get 0.1373 molar? Yes. Again, I did it in 1, but if you did it in 2 steps, that's totally fine. You can totally do this in 2. I like it in 1. It's fine. Okay. Take a look, see if you have any questions on this.
Oh, so our answer at the end is just moles. It's not moles of BA.
It's big M, which means moles over liters.
Right, but we don't have to put the,
Well, I didn't have room.
oh, but we should.
Yeah.
Okay, because that's what threw me off. I'm like, wait a second.
Yeah.
Okay.
Okay,
Did mine in 2 seconds.
are we good? Yes, question? No, you can leave it big M. Yeah, technically big M would be more correct than leaving it moles over liters. Yeah, yes. So I have, this is 4. Because number this 0 doesn't count. It doesn't count 1, 2, 3, 4. The decimal place is present in certain side, first non-zero number, so this one doesn't count. 1, 2, 3, 4. Okay. Well, there's more. Okay, so we can do the same thing. This one is just a percent yield problem. So now the last one we're gonna do is well, not the last, but close. Same kind of thing we did before. So ammonia is produced using the Haber process, which is hydrogen and nitrogen goes to ammonia. Now, what is the percent yield? So I gave you the formula for percent yield. Produced from 15 kilograms each of H2 and N2, if 13.7 kilograms of product are recovered. Okay, so I want you to think about this one for a second. Put the numbers that were given in this problem, put them on this balanced chemical equation. So step 1, I want you to do that. Put the numbers where they go on this balanced chemical equation, and then we're going to start the problem. But that's our first thing, is put them where they belong on our roadmap. Okay, do we have our numbers on? Okay, so let's see if we got them in the right place. 15 kilograms, so 15 kilograms of this, 15 kilograms of this, and 13.7 kilograms of this. Do we get all of our numbers in the right spot?
Yes.
Okay, so we want percent yield. So percent yield is the actual yield over the theoretical yield. Are any of these an actual or theoretical yield? Any of those 3 numbers?
The 13.7 is a yield.
Yeah,
I'm
this.
trying to figure out which one, because I labeled it as actual, but now I don't know.
So this one, so remember, the 13.7 is a product, and products are yields. So 13.7 is either the actual yield or it's the theoretical yield. Which one do you think it is? So remember, the theoretical yield is the one that we get when we look at the periodic table or use our calculator. For 13.7, do we need to use our calculator or look at the periodic table?
It was
No,
given
because
to
they
us.
gave it to
Okay,
us. So
okay.
that makes it the actual
Okay.
yield. So 13.7 is our actual yield. Not supposed to say a K, sorry. This is our actual yield. Okay, which means we need our theoretical yield. So our theoretical yield, so that's the amount of product we get when we calculate it. So how are we gonna figure that out? Because we're given two reactants here. What are we gonna have to do? When we're given two reactants, what kind of problem is this? It's a limiting reactant problem. So what are we gonna have to do with those two reactants? Convert them both to product. So we're gonna have to convert hydrogen to product and ammonia to product. How are we gonna know which one we're gonna use? The smaller number. Yes, so I'm gonna give you a few minutes to work on this, and this will be our last one.
I need markers.
Yes, you definitely need lots of paper and lots of space for these problems. Okay, so here's one of them. Yes. And again, I put these in scientific notation. This is kind of at the limit where maybe you don't need to put these. You could have left these out of scientific notation for your answers for these two. Okay, how did we do? Well, hold on. No, hold on. Let's try this again. Okay. How do we do?
Someone take a picture of this.
Yeah, feel free, take a picture. How?
That's where everybody's at. Okay.
Okay, so if you see this, do you see where any mistake happened? If you made a mistake on these? So again, we were going from grams to grams, which by the way, I just converted it, because I didn't have room. I converted my kilograms to grams before I started. I just didn't have room. It would have been the font's already tiny. But since we went from grams to grams, look, we have 1, 2, 3 conversions. Every time we do grams to grams, 1, 2, 3 conversions. Every single time. Okay. So one of these is real. One of these is not. Which answer is the real answer? The smaller one, right? This never happened. So what would be our limiting reactant? Yeah, the thing that we started with. So N2 would be our limiting reactant. It's the thing you start with ends up being your limiting reactant. But we wanted percent yield. So this 1.82 times 10 to the fourth, this is our theoretical yield. So remember, whenever you have to look at the periodic table or use your calculator, you're calculating a theoretical yield. That's what we've been doing every time. We just didn't call it that, but that's what you were doing. So that one goes on the bottom. The actual yield, now I put them both in grams. You could have just left them both in kilograms. I just didn't want to go back. But no matter what, you end up with 75.3%. You could have done these in kilograms. So you could have just had 1.13, 13.7, 1, 2, 3, 4, 1.37 kilograms over 1.82 kilograms times 100, you get the same thing though, 75.3%. Either of those. I just didn't want to go back to kilograms. I wanted to stay in grams, either or. Okay, so it's a lot. Yes. Definitely a lot. Okay, any questions on these problems? So this is using theoretical yield and percent yield all in one problem. So there's a percent yield down here at the bottom. Yeah, it's our actual over our theoretical. So when we look at our percent yield here, well, it's not. Here's our actual yield is on top and our theoretical yield is on the bottom. Okay, so, and yes, questions. So this is what I said, like this here is scientific notation is kind of like at the limit of scientific notation. So the only time you have to put in scientific notation is when the number is giant. At 10 to the 4, it's not really giant yet. At 10 to the 5, I would put that one in scientific notation. If you're having trouble keeping track of the digits, time for scientific notation. Now, there is one more problem, but we'll do this one next week because your brains are mush. But if you want to take a look at this one, we're gonna start with this one next time. Yes.